So, this is the course of Newtonian mechanics with examples. In last week, that is the third week, we started studying the statics problems where the systems are at rest in mechanical equilibrium. So, this week we shall continue studying those problems with different approaches. So, in the last lecture we started discussing the example of an important practical engineering structure which is called the truss or a framework. So, just quickly we described few examples and defined the problem that we want to analyze. So, today we are going to first we are going to take an example to go step by step and understand how to analyze this problem. So, this is the problem that just quickly let me recall how we define this problem. So, we will assume that there is some structure like a bridge and the whole structure is at rest, so that we can apply the conditions of force and torque balance, and there are two rules that you need to remember, that total force on any single beam is 0 and the total force on any joint or support or node is 0. So, this is also called the strategy that we are going to use is also called the method of joints. And one more important point, that the external loads are given and our goal is to find the internal tension forces in each beam and the contact forces at the joints. So, here is an example of a simple bridge. So, this is a very kind of a toy model of a bridge. So, this is a bridge which is this type of bridge is called I think it is called a cantilever bridge. So, this is different from a suspension bridge which you can think of as a hanging cable. So, here this bridge is supported on both ends and it is a very simple structure. So, this you can often see like a railway bridge in our country. So, this is supported by 3 equilateral triangles which is made up of 1, 2, 3, 4, 5, 6, 7 beams. So, assume that all 7 beams are massless and the connection between any two them is a hinge. So, these are like pin joints. So, the supports are like pin joints. Now, there is an external load, a car of, so this black object is a car of mass m which is standing still at the middle, precisely at the middle of the bridge. Now, given this situation, find the tension T in the beams. So, this is the question. Now, it is also given that we should assume that the supports at the end. So, these are the supports, the joints that supports the bridge at the two side. There is no horizontal forces. So, this is like a roller type support. So, how to solve this problem? So, the first thing that we should note is that we should start by choosing our system. So, in this example, we are going to choose the entire bridge as our system. Now, if the structure is very lengthy or complicated, then you can also choose a section of your framework as your system. Now, we note down two important clue given in the problem is that the all beams are massless, which means the tension is uniform along the beams. So, all the tension forces are uniform along the beams. Now, there is this external force. What are the external forces? So, now once we determine the system, then automatically we also everything that is outside our system is our surrounding. So, this load is not part of the system. So, this car which is of mass m is not part of our chosen system. So, when you analyze the problem, so you should make this kind of mental map to sort of highlight this point. Now, once we define the system, then we need to list out all the interactions, what are the forces interacting in the system. Now, here let us say if I take the entire bridge as the system, then the forces are actually, there are some force as we show in this picture. So, there are force on, so this joint, this is a support. So, it exerts some force on this bridge, and similarly on the other side, let us call that Q. So, in this case also it exerts some force on the bridge. On top of that, the car is also exerting a force downward on the bridge, that is a contact force. Now, since the, so this force is also unknown, but we can determine the contact force, you can replace it by the weight of the car. Why? Because suppose this is my car, and then let us draw the free body diagram of the car. So, then on this car there are two forces. So, one force, it's its weight mg. So, then this is an interaction with the surrounding of the car. In the surrounding of the car, not the bridge, but the car, there are two important objects. One is the earth, which is pulling it, exerting a force, gravitational force mg, and the other is this. So, the car is also sort of interacting with the bridge, and let us say this force is N. So, then so this force is a contact force by bridge. Now, I draw it more clearly. So, this force is a contact force on the car, and I also draw another force. So, this force is the Newton's third law pair of this contact interaction between the car and the bridge. So, this is the force on the bridge by the car. So, this is the force which is required for our analysis. Now, if the car is at rest, then we know that the total force on the car is 0. So, that means N minus W must be 0, which means N equal to W. So, this is the magnitude of the contact force, and hence we know the magnitude of the force on the bridge by the car, which is also W, that is mg, and hence now, and the direction must be downwards. So, now, so the direction is downwards. This is important because, so in this problem of Truss, the directions can be tricky. This is important. So, you must pay close, and that is why in order to reduce avoid confusion, you must have a clear idea about, define your system very clearly. Only then the directions will be very clear. So, if I take the whole bridge as a whole as my system, then these are the external forces. In the given information, and I have drawn this diagram here to denote these external forces by the blue. Now, so this is given. Now, the problem asks to calculate the internal forces, the tension forces in the beam. Now, in this case, in order to the strategy is, so now you sort of take each node as your system, and each node as your system. If you take each node as your system, and then we need to draw the free body diagram of that particular node and apply the conditions of force and torque balance, and then we can write down the some equations of the unknown tension forces, and once we find all the equations, then we can solve them to calculate the unknown forces. So, this is the general strategy. So, now which node you should start with? You should start with a node on which the external force is acting. That always simplifies. That is a important trick to remember. So, here I am starting on this particular node. Now, in this type of frame Truss problem, what is tricky is to get the direction of the internal force tensions right, which means at a given node whether the force and along the beam are along like away from the node or towards the node. So, whether this is in our language defined earlier, whether this is a tension force or a compression force. Now, in this particular case, let us say we take A, the node A on which where the car is standing, let us take that as our system. Then there are 3 forces acting at this node. One force is evidently the force on the bridge, on the support by the car, which we have just found. This is equal to mg and it is directed downwards. The second force is the tension along the beams. So, there are 2 beams which are there are 1, 2, 3, 4 beams which are along connected at this node A, but in the given problem it is given that in these 2 beams there are no horizontal force, it is given in the problem. So, we ignore these 2 beams. So, then only 2 beams remaining, and let us consider that the tension force in the beams are T1 and T2 respectively in beams AB and AC. Then from this picture by geometry, so all of these beams are of equal length. So, all these triangles are equilateral triangles. So, these angles are 60, all the angles are 60 degree. Then, so we consider the force balance equation for this node A. So, to balance this force mg which is downwards, intuitively it is clear that the direction of this force T1 and T2 must be away from the support A. So, this the horizontal component of this T2 must be T2 cos 60 degree, because this is 60 degree, and similarly the horizontal component of the force T1 which is acting in the beam AB should be T1 cos 60 degree, and since the node is at equilibrium. So, that means if we do a horizontal force balance, so what we find that these 2 forces must cancel each other. So, that is T1 cos 60 degree must be equal to T2 cos 60 degree, and it follows that these 2 tension force are equal in magnitude and let us call that T. Now, if we do a vertical force balance, it is a force balance in the vertical direction. So, then we see that the vertical component of this force T1 is, so this is T1. So, this is T1 sin, so this is 60 degree. So, this is T1 sin 60 degree, and similarly for T2 this is 60 degree. So, this is T2 sin 60 degree, and there is a force mg downwards. So, these 2 vertical components must be balancing this downward force mg by the car on the bridge. So, this is not the weight of the car, it is the contact force by the car on the bridge. So, then we can write down the vertical force balance condition, and if we apply that T1 is equal to T2 which is equal to T, then it follows by solving this equation that this unknown, the tension at the each of the tension T must be equal to mg by root 3. Now, I will give you as an exercise that you can sort of see, you can verify. Now, take this another nodes, node B as your system, and then there are 3 beams which are connected at node B, and I have shown. Now, remember that if we apply our rule 2, that so the if we want to know the force acting on the node B, then we need to determine the force, direction of force at the node B by the beam and on the beam. And if we apply the force balance condition on the beam AB, then total force by the beam must be 0. So, that means if it is experiencing if the beam is experiencing, so then if we know the direction of the force T1 at the node A, then the direction of the force on the node B, which is the other side, other end of this beam, must be opposite, and it must be equal in magnitude as well. Hence, if we know this force, then we immediately know the magnitude of this force must also be mg by root 3. And similarly, you can consider the other nodes, and each of the nodes. So, take B and then take C, and then write down the force balance conditions, and from which you can get the what are these tension forces in the other beam elements. So, I will leave as an exercise another problem. So, this is a slightly more longer, slightly more complicated truss with same number of beams, 1, 2, 3, 4, 5, 6, 7. So, same number of beams, but in this case, instead of the total external forces are slightly different. So, the supports are now no longer at the 2 ends and the base, but they are on one side at the 2 ends of this beam D and E. So, this is the difference. And the other difference is that, like in the previous example, you have an external force which is acting on this framework at the node C, which is 20 kilonewton, but in addition there is another external force which is acting at the end A, which is 30 kilonewton. So, note that the arrows represents, the red arrows represents the force, external force, both in magnitude as well as direction. So, the question is that given the structure and the supports, compute the force in each member of this loaded cantilever truss. So, this is kind of a bridge or a cantilever which is supported. So, cantilever is a structure which is supported at one end, and it is kind of hanging, the other part is hanging in the air, and by the method of joints. So, one thing you must remember here is that in general you should not assume that the tensions in all the beams are same. You have to assume, like we did here when we started, that the tensions are different, and then if the problem shows, the calculation shows that the tension turns out to be same, then it is well and good. So, I am not going to solve this problem, because this is meant to be sort of give you an exercise, practice to sort of write down the force and torque balance conditions. So, you do not need any torque balance conditions here in this particular problem at each node, node by node. So, here instead I am going to give you a few hints of how to approach this problem. So, first, if you take your define your system as before and the surrounding. So, let us say you take the entire structure ABDE, ABDECA as your system, and that will give you an idea of what are the external forces acting on this framework or the bridge. So, there are of course the force T, which is because of the support, this particular support which is supporting the structure, and then there are other forces due to the other support at the point at the support E, at the node E. Now, so let us so I will give you a hint. So, assume that the supports, the nature of the the contacts are the supports, this support and this supports are such that, I mean, the support at D and support at E is such that these are the directions of those external force. Let's so assume that, you can assume that. So, there are at D there is only one force which is going along the length of this beam. At the joint E, the contact force has two components in general. One which is a, let us define our x axis, this direction as our x axis and this direction as our y axis, and then this is a horizontal component and a vertical component. So, now all you need to do is to go node by node, take each node and then apply the free body diagram at each node and write down the force balance conditions and make a list of which is the unknown. So, the tension forces are unknown and the external forces are given, and then you have an equation and solve this equation to determine the unknown tensions. Now, here is a hint that which node you should start with. So, again you should start with, it is easier to start with nodes where the external forces are acting. So, let us start at node A and write down the, take the node A as your system. So, this is connected by two, let me complete the beam structure. So, it is connected by only two nodes, two beams. So, write down the free force balance equations at node A, then go to node B, then go to node C and then go to node E instead of D. So, if you follow the node, your calculations will be simple. So, we shall continue discussing some more aspects of this truss structure in the next lecture. Thank you.